Hi guys, welcome to the Book of Flight, a side project I've been working on for the past few months. It's all about building airplanes and diving deep into the world of aviation. In today's video, I'm here to take you on a thrilling journey. Our main goal is to introduce you to the application and offer you some valuable insights into the fascinating engineering that goes into making these incredible flying machines. Let's start with the basics. How do airplanes fly? Imagine a simple rectangular plate in a strong wind. As you hold it, you'll notice a force acting on it. When the plate is perfectly parallel to the airflow, that force is minimal. However, as you start tilting it backwards, something interesting happens. The force increases rapidly and remains perpendicular to the plate. You may ask, what's the source of this force? Let's stop the wind for a moment. Although the air appears stationary, its molecules move a lot. When they happen to collide with our plate, they bounce off and create a tiny force. On a larger scale, we can observe that as pressure. Without any airflow, the forces exerted on the plate by the atmosphere cancel out, and the net force is zero. When we turn the wind back on again, more air particles start to collide with the exposed lower side, and the pressure goes up. The other side is partly shielded from the flow, so fewer collisions result in lower pressure. The same applies to the shorter sides of the plate. When we add up all those vectors, we get the aerodynamic force we saw earlier. Usually the rotation axis of the wing is not positioned at the center, but at around 25% of the length. This, however, creates a torque and the plate starts to spin. We actually need something to counteract it, and that is the pitching moment. We'll skip it for now to simplify things a bit. The difference in pressure greatly influences the flow around the plate. You may have noticed the air on the top is actually moving faster than on the bottom. We can explain this change using the Bernoulli's principle. This is its standard form. In this example, the height difference is negligible, so we can skip the second term. The sum must remain constant, so when we decrease pressure, the speed has to increase. There is another explanation of lift based on the Newton's laws. As air flows around the plate, it gets deflected downwards. According to Newton's second law, this requires a force applied to the flow by the plate. Thanks to Newton's third law, the plate experiences an equal and opposite force. We can break it down into two components, one that acts vertically, which we call lift, and another that aligns with the airflow direction, named drag. Even a simple plate can generate lift, albeit with a trade-off, in the form of substantial drag. But here is where things get exciting. There are better shapes out there. Take for instance this aerodynamic profile. Not only does it generate more lift, but does so with such minimal drag that we have to scale it tenfold, just to visualize the vector. There is a common misconception regarding lift, which you might have heard of. It's based on the assumption that air particles require equal time to travel along the upper and lower surfaces of the airfoil. Supposedly, this forces the air above to speed up, because it has a longer way to go. Using Bernoulli's principle, we should conclude that the pressure will decrease on the upper surface, effectively pulling our shape upwards. But here is a catch. There is no physical principle that would imply the equal transit time. It would also mean that our plate cannot really produce lift, because it's symmetrical. Air would have nowhere to speed up and generate a pressure difference. These are the components of an airfoil. An outline, a chord line, which is connecting the leading edge at the front and the trailing edge at the back, and a camber line which lies right in the middle between the upper and lower surfaces. This is a NACA 2412 profile. It belongs to one of the most well-known airfoil families, the NACA 4-digit series. This name is a simple mathematical relation. The first digit describes the maximum camber as a percentage of the chord. The second, position of set maximum camber. While the last two digits describe max thickness of the airfoil. For 4 series NACA airfoils, it just so happens to be at 30% of the chord. Now, let's choose our airfoil. Here, the charts on the right display the values of aerodynamic coefficients of lift and drag. When we hover over the charts, we can observe how the data influences the airfoil on the left. We can click to lock our markers on the charts to enable some new options. At this point we can change the airfoil and compare how it behaves in a similar setting. We can see how increasing the profile camber corresponds to an increase in lift created by the airfoil. More camber means more air deflected and the lift is higher. This also means that we need a shallower angle of attack in order to generate the same lift force. This gives an advantage, as at the same time the drag decreases. Now we're going to gingerly increase the angle of attack. At some point, the air will start to separate from the profile. The drag will increase significantly, and there will be a sudden decrease in lift. This is a stall. The plane may become unresponsive as it progresses. Bear in mind that the drag was scaled up for a clearer comparison. This is a symmetrical airfoil. It has zero camber and produces no lift at a 0-degree angle of attack. Its aerodynamic properties are also symmetrical. Another crucial factor to consider is the Reynolds number of the flow. It's a dimensionless value that predicts whether a fluid flow is turbulent or laminar. It can completely change the characteristics of the airfoil. In a slower flow, the coefficient of drag gets bigger due to a higher influence of the friction drag on the total drag force of the airfoil. Well, I could scale the vectors down a bit. But let's see some other profiles. We have everything you want. The thin, the chunky, or even the flat ones. Well, that's a lot of drag. Technically, it should still fly better than a brick. Spoiler alert, it does! Anyway, you can get some more info when you hover over the formulas. The profile data comes from wind tunnel tests documented in NACA 824 report. NACA, or the National Advisory Committee for Aeronautics, founded in 1915, pioneered numerous technological advancements during World War II in the fields of airfoil design, supersonic flight, and rocketry. This eventually led to the formation of NASA in 1958. There is so much more to cover in terms of aerodynamic profiles and how they evolved over time, and we'll try to come back to this subject sometime in the future. I'm considering adding a particle fluid simulation to better visualize some of the concepts the newer profiles introduce. Leave a comment if you'd like to see that. Now, let's go back to the business. When we want to maintain level flight, the forces acting in the vertical direction must be equal. This means in order not to fall down, we need to keep a specific coefficient of lift equal to 2 times the weight divided by the density of air times velocity squared times wing surface area. Here we can see that making the plane heavier or lowering the speed will require a steeper angle of attack. The drag experienced by the aircraft is directly proportional to the square of its velocity. Consequently, when we double our speed, the drag will increase 4 times. Reducing the speed can lead to a stall, resulting in a rapid unscheduled disassembly when we meet the ground. There is still hope, however, as we could do what any sane person would do in this situation. We throw our passenger out the door. Wait, what do you mean it didn't work? Ah, my bad. Just give it some gas and we'll be fine. Up until this point, we studied the aerodynamics of a 2D profile. It happens to be the same for a wing with an infinite length or one inside of a wind tunnel. As air flows around the wing, it creates a low pressure area at the top and a high pressure area at the bottom. This difference results in a flow from the lower surface to the upper, especially around the wingtip. This, combined with the speed of the flow, creates a vortex. When we increase the angle of attack, the vortex intensifies due to a higher pressure difference between the surfaces. Conversely, raising the speed decreases the size of the vortex. The airflow behind the trailing edge is deflected downwards, which we refer to as downwash. In a 2D context, lift remains entirely vertical, and there is no generation of downwash by an airfoil. However, when we transition to a 3D wing, downwash angles the relative airflow backwards. Lift is always perpendicular to the airflow. The X component of lift is referred to as induced drag. It's worth noting that, unlike parasitic drag, induced drag decreases with speed. It's actually inversely proportional with the square of the velocity. The Y component represents the true lift. Due to the presence of downwash, the true lift is slightly smaller, which necessitates a steeper angle of attack to achieve the same lift in a 3D scenario. We can see that on the next step. Here on the left chart, we can see how lift is essentially delayed by the presence of wingtip vortices. Due to the pressure mixing at the wingtips, we won't create as much lift, so for a given angle of attack, the coefficient will decrease. It's worth noting how big of an impact induced drag has on a wing. For a typical jetliner at cruise speed, it can account for around 40% of total drag. Nowadays, aircraft designers employ innovative aerodynamic solutions like winglets to enhance overall efficiency. They use super fast computers to simulate the flow and extract every little bit of performance from the plane. But let's not get ahead of ourselves and start with choosing the shape. Use the slider to select from a range of presets, or interact directly by clicking and moving the spheres on the outline. You can input precise values in the measurements, or utilize the built-in arrows for adjustments. On the left side of the outline, you'll find some formulas you can hover over. First up is the aspect ratio, calculated as the wingspan squared divided by the surface area. Next we have the taper ratio, which represents the ratio of the tip chord to the fuselage chord. The last one is the mean aerodynamic chord, or MAC in short, which serves as a 2D representation of the entire wing. It's really important for both constructors and pilots. All forces acting on our wing can be reduced into a single force and a moment, positioned at approximately 25% of Mach. Another critical factor is the location of the center of gravity, also expressed as a percentage of Mach. It will play a crucial role in the stability of our plane, but we'll concentrate on that in the future. Interestingly, an elliptical wing design has slightly less drag compared to a trapezoidal wing with the same aspect ratio. This is due to the smaller induced drag on elliptical wings, shedding light on their popularity during World War II in iconic aircraft such as the Spitfire. If you prefer freedom units, you can switch to them in the settings. I won't judge you. With the wing completed, it's time to turn our attention to shaping the fuselage. While this is a work in progress, our potential is limitless. We can easily simulate various aircraft configurations, from a simple plane to a twin fuselage biplane, provided there is enough research to support the modeling. But that's just the beginning. With the power of programming, we can push the boundaries even further. Imagine the possibilities. What if we put a Tesla engine or a big V8 inside? It could result in an incredible speed and endurance, or perhaps not even fly at all. The journey continues, so stay tuned for the upcoming adventure as we delve into the next steps of our design process. In the meantime, if you'd like to experiment yourself, the link to the application is down in the description.